Welcome back to EMWORKS video series. In this short video, we shall show you how to optimize eddy current brakes using EMWORKS simulation. Eddy current brakes use electromagnetic fields to decelerate objects without contact, inducing eddy currents that create an opposing force, converting kinetic energy to heat, offering a reliable, maintenance-free alternative. Designing an eddy current braking system is complex, requiring precise calculations. Engineers must determine the torque for passive, active, and hybrid systems, considering the relationship between braking torque and speed. Key factors include magnet type, arrangement, number of poles, and excitation current. Effective design ensures smooth operation, manages deceleration torque, calculates dissipated power, and monitors temperature rise in conductive parts. EMWORKS simulation helps overcome eddy current braking design challenges by accurately modeling magnetic fields, eddy currents, and thermal effects. It enables engineers to optimize magnet placement, manage heat dissipation, and select suitable materials. This ensures efficient braking torque, power dissipation, and temperature control, leading to reliable and high-performance eddy current braking systems. Let's look at the magnetic flux density in an axial permanent magnet braking system using EMWORKS. The magnetic field circulates through the iron components, forming two loops. Each loop contains two poles, essential for effective braking. Let's look at the eddy current density across the copper disc. Rotation within the magnetic field induces eddy currents, strongest between the magnetic poles. This concentration ensures efficient braking, providing consistent force and highlighting the system's optimal design and functionality. Braking torque versus rotor speed. Eddy currents oppose the motion, generating braking torque that stops the disc's rotation. The figure shows torque increasing with speed. This relationship is vital for optimizing performance, with comparison against experimental data showing good agreement. Dissipated power versus rotor speed. Dissipated power in the disc is crucial for braking performance. As rotor speed increases, eddy currents generate more heat, leading to higher power dissipation. The figure shows dissipated power increasing with speed, highlighting thermal management needs and confirming simulation accuracy against experimental data. Torque versus time for different permanent magnet materials. We investigated different permanent magnets. Neodymium iron boron yields the highest torque but is expensive and heavy. This trade-off highlights the challenge of balancing performance with cost and weight. Alternative materials may offer a more balanced solution despite superior torque generation. Deceleration torque and speed versus time for 3 different RPM. The deceleration torque plot shows that the torque increases from 0 when the brake is activated, reaches a peak, and then decreases until it returns to 0. This decrease in torque occurs as the speed decreases due to the braking force. The interaction concludes when both torque and speed approach 0. The speed plot indicates that, regardless of the initial rotor speed, the rotor comes to a complete halt in approximately 20 milliseconds. The temperature distribution of a double-sided ventilated brake. Temperature rise in the discs due to eddy current losses is crucial for performance and durability. Induced eddy currents generate heat, raising disc temperature. Without proper thermal management, this degrades materials, reduces efficiency, and risks damage. Effective cooling and optimized materials are essential. The plot shows the temperature reaching 84 degrees Celsius in about 90 seconds. Conclusion. This short video details the simulation of eddy current braking systems using EMWORKS software. Examples demonstrate optimizing magnetic fields, managing thermal effects, and selecting materials. Simulations highlight factors affecting braking torque, power dissipation, and temperature rise, validated by experimental data, confirming EMWORKS accuracy and reliability. Thank you for watching and stay tuned for future videos from EMWORKS.